The third colligative property is depression in freezing point. The symbol of this is delta TF. We know that the moment the non-volatile solute is added to the liquid solvents, what happens is the vapor pressure of the solution becomes less than the pure solvent. This we already know. But what is the effect of this thing on the freezing point of the solvent is, yes, this is the thing which is known to be known, which is actually to be known. The freezing point is basically the temperature at which we already know the solid and the liquid states are in equilibrium with each other. But from this graph, one must understand, we have taken the pure A as a solvent, B as a non-volatile solute. We first took the pure solvent and at a certain temperature, and we started decreasing its temperature from here, this side to this side. We are coming from the right to left. Now, as we decreases the temperature of the pure solvent, the vapor pressure also decreases, and the graph follows this curved path, and there comes a peak here. Now, when we drop a perpendicular, we can find out at what temperature this peak comes. This temperature is called Ti, and this is called freezing point of the pure solvent. Now, the question comes is, this is the temperature at which the solvent, the solid solvent and the liquid solvent will be in equilibrium with each other. But remember, we are not plotting the solid or the liquid states of the solvent along the y-axis. What we are plotting is the vapor pressure. So, what is the freezing point is? It's the point at which the vapor pressure due to the liquid state equals to the vapor pressure due to the solid state. I'm repeating again. At this point, what we find is the vapor pressure of the liquid state is equal to the vapor pressure of the solid state, and that point is called the freezing point. Now, once we understand this, we can make out when we add a non-volatile solute to the liquid solvent and forms a solution, the vapor pressure of the solution gets lowered and it is found to be less than the pure solvent. Now, when the vapor pressure of the solution is less, definitely the equilibrium which the liquid state now will establish with the solid state's vapor pressure, or the point at which the vapor pressure due to this liquid state will equal to the original solid solvent, that gets lowered, and as a result this decrease results in the depression in the freezing point. This is very clear from the second graph. When we added a B non-volatile solute to the same solvent, liquid solvent, and forms a solution, where at this temperature the vapor pressure is found to be nearly this much. When we started decreasing the temperature, the graph follows this path and it comes in contact with the solid solvent graph at this point. So, the peak and this graph of the graph of the solution comes at this point. If we plot a perpendicular, we can find out where this peak comes. This comes at around Tf. Now, Tf is what? Is the freezing point of the solution. So, what we can find is the freezing point of the solvent decreases from Ti to Tf, and this decrease is called delta Tf. Now, why there is a decrease? I am repeating again, because now since the vapor pressure is already of the liquid solution is already less, the point at which it becomes equal to the solid vapor pressure of the solid solvent will also be what? At a lesser temperature, at a lower temperature. It gets decreased, and that is why this decrease or depression takes place. So, this depression in the freezing point of the solvent is called depression in the freezing point, or delta Tf. Now, as it is clear, this delta Tf will be equal to Ti minus Tf, because initial temperature is higher, is a larger value than the Tf or final temperature. So, this is equal to Ti minus Tf, and experimentally it was determined that this delta Tf is proportional to m, where m is the molality of the solute in the solution, and this proportionality is opened by a constant which is called Kf, and the formula becomes like this, which can be expanded as Kf molar weight of the solute, molar mass of the solute, into 1000 upon weight of the solvent. So this is what is the formula is, and remember this Kf is called molar depression constant or cryoscopic constant or depression in the freezing point constant. So it's the same. This Kf is very similar to the Kb which we have studied in the elevation in boiling point. But yeah, yes, this is what is the formula is. The cryoscopic constant or molar depression constant, this is Kf, is its unit can be determined like this. Like this, delta Tf we know is equal to Kfm. Therefore, this Kf will be equal to delta Tf by m. So its unit will also be Kelvin kg per mole, which is very similar to the unit of the ebullioscopic constant or Kb. And to define Kf, if we take molality as 1 mole per kg, we find that Kf become equal to delta Tf. So how we can define is that it is the depression in the freezing point of the solvent when 1 mole of a solute, non-volatile solute, is added to 1 kg of the solvent. And remember, as Kb, every solvent has its own Kf value, which is actually determined by the formula, which is very similar to the Kb formula. Only difference is that it is RT square m upon 1000 into enthalpy of fusion. You remember, in case of Kb, we were having here enthalpy of vaporization. Here we have enthalpy of fusion, the amount of energy required to increase the temperature of 1 mole of a solid substance by 1 degree Celsius to a liquid state, to convert it into a liquid state. So amount of heat fusion, the enthalpy of fusion is involved here. R is the universal constant, T is the freezing point or melting point of the solvent, m is the molar mass of the solvent, so it's Ma 1000 upon enthalpy of fusion. So this is what is the formula is. We can find out the Kf, and like the Kb, every solvent has its own Kf value. Like Kf for water is 1.86 Kelvin kg per mole. It means what? Whenever 1 mole of any solute is added to 1 kg of the water, the depression in the freezing point equal to 1.86 takes place. So this is what is depression in the freezing point is. As we know, depression in the freezing point is a colligative property. It can be used to find out the molar masses of the solutes which are present in the solutions. So let us see a numerical how it is done. The numerical is find the molar mass of a non-volatile solute when 1 gram of it added to 50 grams of water results in the freezing of the solution at 272.5 Kelvin. The depression in the freezing point constant for the water is 1.86 Kelvin kg per mole. So from the data it is given that the Tf freezing point of the solution is 272.5 Kelvin, and we know the freezing point of the pure solvent, pure water, is 273 Kelvin. So we can make out from here that the delta Tf is Ti minus Tf, which is 273 minus 272.5, which is 0.5 Kelvin. So this is what is the value is. This is now known to us. And then what other else are given? The weight of the solvent is given as 1 gram. Weight of the solute is given as 1 gram. Weight of the solvent is how much? Is 50 grams. Molar mass of the solute is to be determined, and the Kf is already given as 1.86. So let us put these values in the formula. The formula we know is delta Tf Kf, weight of the solute, molar mass of the solute into 1000 upon weight of the solvent. Delta Tf is 0.5, Kf is 1.86. Weight of the solvent was solute was 1 gram. Weight of the molar mass of the solute we wanted to know. It is 1000 upon it's 50. So it's how much is 20. So what we get is MB will be 1.86 into 20 upon 0.5. So it will be almost 40. It will come out to be 74.4 grams per mole. So this is what is the molar mass of the solute which was present in the solution. So this is how we can use this data or the formula or the depression, the freezing point to find out the molar masses of the non-volatile solutes present in the solutions.